In 5G, we already move into mmWave. Now, for 6G, research is moving toward 100 GHz, 140 GHz, even close to 300 GHz. But this is not just more bandwidth. It introduces completely new RF challenges. Today, we will discuss what really changes when we move into sub-terahertz frequencies, and what this means for RF engineers. 5G mmWave uses 28 and 39 GHz. Bandwidth is already large, but still limited. To reach extremely high data rates, hundreds of gigabits per second, researchers look at sub-terahertz bands. One key candidate is D-band, around 110 to 170 GHz. But moving up in frequency changes everything in RF design. Today, let's talk about what really happens when we go beyond the mmWave into sub-terahertz spectrum, and what this means for us as RF engineers. First, what do we mean by sub-terahertz? Normally, we talk about the frequencies from around 90 GHz up to 300 GHz. One important band is D-band, which is roughly 110 GHz to 170 GHz. 140 GHz is often discussed as a candidate for early 6G research. Why this range? Because there is much wider contiguous bandwidth available. Tens of gigahertz bandwidth is possible. Data rate can go hundreds of gigabits per second. But spectrum availability does not mean it is easy to use. Physics doesn't change because we want higher data rate. Let's review one basic equation: free space path loss. Free space path loss is proportional to frequency squared in dB form. Free space path loss increases with 20 log frequencies. So if we compare 28 GHz and 140 GHz, 140 divided by 28 is 5. 20 log 5 is about 14 dB. This means at the same distance, we'll lose 14 dB more signal power. 14 dB is almost 25 times power differences in linear scale. To compensate this, we need higher antenna gain, higher transmitter power, or shorter distance. This already changes link budget strategy. Now, let's talk about atmospheric absorption. At sub-terahertz frequencies, signal loss is not only free space spreading. Molecules in the air absorb energy, especially oxygen and water vapor. Their absorption peaks at certain frequencies. For example, around 60 GHz, we already know oxygen absorption is high. At higher frequencies, more absorption windows appear. Some frequency bands are beta windows. Some bands have much higher attenuation per kilometer. So, frequency planning becomes more complex. It is not just bandwidth. It is also atmospheric loss profile. For long-distance communication, these absorption effects can dominate. Now, let's talk about devices. At 140 GHz, transistors' performance becomes critical. We care about FT, transition frequency, Fmax, maximum oscillation frequency, gain at operating frequency. CMOS can reach high FT, but available gain at 140 GHz is limited. SiGe BiCMOS is promising. I-on-P HBT technology shows very good high-frequency performance, but the cost is high. GaN is strong for power, but efficiency at a very high frequency is challenging. Also, power added efficiency generally drops as frequency increases. So, we face lower gain, lower output power, lower efficiency. This means more stages, more combining, more heat, which increases complexity and then cost. Let's combine everything. Higher free space path loss, atmospheric absorption, lower power amplifier efficiency, limited device gain. What does this mean? Sub-THz systems will likely be short range, highly directional, beamforming intensive. Very large antenna arrays may be required. Fortunately, wavelength is very small. At 140 GHz, the wavelength is only about 2 mm. That's very small. The good news is we can build very compact antenna arrays, and with large arrays, we get high antenna gain to help compensate for the path loss. But this also creates a new challenge. The beams become very narrow, so beam alignment becomes critical. And when users are moving, mobility becomes much more complex. So, what is the key message for us as RF engineers? Sub-THz is not just an extension of millimeter wave. It changes design philosophy. First, link budget margin becomes extremely tight. Second, antenna gain is not optional, it's mandatory. Third, device selection and packaging become system-level decisions. Fourth, thermal and efficiency constraints may limit practical deployment. In 5G, we already pushed RF design to limits. In 6G sub-THz, physics pushes back even harder. Let me summarize. Sub-THz is not just more spectrum. Physics becomes stronger constraint. High gain array are essential. Efficiency and thermal may limit deployment more than bandwidth. In next episode, we will go deeper into one example. What does it take to design an RF front end at 140 GHz? We will talk about gain, noise figure, packaging loss, and an antenna-in-package integration. If you are working in RF, the future may operate at these frequencies. Better to understand the challenges early. Thank you for watching, and see you in the next episode of 6G RF Frontiers.